So, we're now going to be moving into our very last section of the semester, and please hold the tears. I know it's a real tragedy to be finished after all the work we've put in, but even the best things must end. Where here, we're going to be talking about a thing called the Binomial Theorem first, with a piece of that called the Binomial Coefficient, where for this, we have the notation n above r in those tall parentheses, where for n greater than or equal to r, this is equal to n factorial over n minus r factorial times r factorial, all in that quantity on the bottom. And the book says you should just call this n above r and treats it as its own unique thing until you get to 10.6, which we're not covering here except as extra credit. But those of you who have taken statistics before should have seen this quantity before. You should be at least somewhat familiar with this term, albeit maybe under a different name, where you may have seen this before with a subscript n, a big C, and a subscript r, that is, as n choose r. Because it actually is the same thing, that when we're looking at this binomial coefficient, we're describing the same quantity as n choose r. So when we take this value, you can think of it in terms of counting as representing the number of ways that you can arrange r objects from a total of n, where you do not allow for repetitions and the order does not matter. The way you can think about this in terms of that counting is the total number n things is n factorial. The n minus r factorial on the bottom says, okay, I've picked my n things, I don't want to worry about the rest, so I'm going to shove those off. And then the additional, multiplicational, I suppose, r factorial there as well says, okay, I've got my r things, I've removed the other n minus r of them, but I also don't care about how I select those r themselves. So for example, if I'm selecting three numbers up to 5, 1, 2, 3 is the same as 3, 2, 1 is the same as 3, 1, 2 is the same as 3, 2, 1, which is to say all of those arrangements are equivalent if order doesn't matter, and I don't want to treat them as separate things if that is the case. So I knock them out. And for the record, I've taught this material a fair few times now in stats classes, so if you're having trouble seeing these ideas or you want to see some other context in which they can be approached, let me know and I can point you in the direction of some of my materials for that as well. But for our context here, we're just going to look at a couple of quick examples. So for this, we want to compute the binomial coefficients 8 choose 3, 8 choose 8, and 8 choose 0. Where I'll say that with these, you can do them by hand, and I'm going to show you how to do them by hand. For the record, there are also ways that this can be handled in calculators pretty easily, but because I'm not expecting everyone to have access to a TI-84 or something similar, I'm not going to put too much emphasis on that, though you should be seeing right now at least a quick way to get it. Anyway, if we want to do this, technically showing all this work of factorials, in that first case, where we have 8 choose 3, that will be 8 factorial over 8 minus 3, quantity factorial, times 3 factorial, where the nice thing here is that for one, we can turn that 8 minus 3 factorial into a 5 factorial, and let's remember not to multiply these two in together just yet. We're going to keep them a little bit separated as they are right now, but from this, we can pull out terms from that 8 factorial, and I'm going to pull out a few where it's not going to be obvious why I did this until you see how I write the bottom as well, that we can pull out an 8, a 7, a 6, and leave out a 5 factorial. And then on the bottom, we still have a 5 factorial along with a 3 factorial, but here, we've now got a 5 factorial and a 5 factorial. Those will cancel, and we'll be left with 8 times 7 times 6 over 3 times 2 times 1, which is also 6. So we'll just have 8 times 7, or 56. And this is usually how any type of factorial or combination, or in other contexts, permutation, computation goes. We just see how we can find some matched up factorial terms, cancel them out, and we're left with hopefully something, if not easy, at least a bit more manageable, where, again, if you want to think about this in terms of arrangements, if we're taking 8 things and we're picking 3 of them, we have 8 options for the first, 7 for the second, and 6 for the third, but we have 3 ways to pick that first that don't matter, 2 ways to pick the second that don't matter, and then the last one gets squished, but it still doesn't matter, so we want to knock that out, and we're just left with 56 ways that we can arrange without concern for order. In our second case, where we are taking 8 above 8, or 8 choose 8 if you prefer, that will be 8 factorial over 8 minus 8 factorial times 8 factorial. Well, that's quite a lot of 8s. But what we're going to see here is we have 8 factorial over 0 factorial times 8 factorial. The 8 factorials will still cancel, and we'll be left with 1 over 0 factorial, which might seem like it means it's time to panic because we're dividing by 0 somehow, right? Aren't we dividing by 0? Oh no, oh no, no. But let's take a deep breath and remember that earlier on, I talked about how you can think of 0 factorial as being an arrangement of nothing. That is, if you arrange 0 things, you technically can do that in one way. I also mentioned that there are constructions where, for convenience, we have to make 0 factorial equal to 1, and that's one of those cases here. So we just get 1. And that should also make sense if we think counting-wise, that if we want to pick 8 things from a group of 8 things where we don't care about order, there's only one way to take everything. If we don't care about order anyway. So it's just 1. And then finally, for our third case, it goes in a similar way, but, well, we'll see that how we get there is slightly different. Anyway, for 8 choose 0, we have 8 factorial over 8 minus 0 factorial times 0 factorial, where again, 0 factorial is 1, thankfully, and otherwise we get 8 factorial over 8 factorial, which is just 1, which should make sense, because no matter how many things we have to pick from, there's only one way we can pick none of them, by picking none of them. So, really, anything choose 0 is 1. And in fact, there are a couple of nice patterns here that for any number n choose n is equal to n choose 0 is equal to 1, which should make sense, while n choose 1 is equal to n. And I'll leave you to check this. I'm probably going to make it an extra credit question actually for you to argue in terms of counting why this happens. It should make good sense if you think about it for a second. But anyway, this is how we handle binomial coefficients, which are nice in and of themselves, especially for counting things, but really what we want to get to is the idea called the binomial theorem, which gives us a way to talk about any power of a nice two-dimensional algebraic term that we'll see next.